So this talk could be a little challenging because we're going to see some stuff that tickles our brains and some images that will be a little disturbing, although it won't really be clear why they're disturbing. And we'll talk about why. And we'll talk about some things that we don't usually talk about. And all sorts of stuff sort of pours out when you open locks like that. And so if you can be here for it, I would love that. And if you can't, take care of yourself. Otherwise, hello. My name's Ashi, and as Brandon mentioned, I am a senior software engineer at GitHub. And that really has nothing whatsoever to do with the talk that you're about to hear. Because today, I want to talk to you about a hobby. I'd like to share some of what I've learned at the intersection of computational neuroscience and artificial intelligence. So for years, I've been fascinated by how we think, how we perceive, how the machineries of our bodies creates subjective experience, and why our experiences are shaped in the way they are, why we feel joy and why we suffer. And for years, I've been fascinated by machine learning and AI, and I think we all have. We're watching these little machines begin to approximate the tasks of cognition in sometimes unsettling ways. And so today, I want to share some of what I've learned. Some of it is solid research. Some of it is solid speculation, and all of it speaks to a truth that I have come to believe, which is that we are computations, are worlds created on an ancient computer, powerful beyond imagining. So let's begin. Part 1, hallucinations. This person is Miquel Pereiro Nieto, and he has something to show us. It starts with simple patterns, these splotches of light and dark, like images from the first eyes. These then give way to lines and colors, and then curves and more complex shapes. We're diving through the layers of the Inception image classifier, and it seems that there are whole worlds in here. Shaded, multichromatic hatches, the crystalline farm fields of alien worlds. Cells of plants. To understand where these visuals are coming from, let's look inside. The job of an image classifier is to reshape its input, which is a square of pixels, into its output, which is a probability distribution. The probability that the image contains a cat, the probability of a dog, a banana, a toaster. It performs this reshaping through a series of convolutional filters. Convolutional filters are a lot like Photoshop filters. Each neuron in a convolutional layer has a receptive field, a small patch of the previous layer of neurons from which it's taking its input. Each convolutional layer applies a filter. Specifically, it applies an image kernel, a matrix where each number represents the weight of a corresponding input neuron. So each pixel in a neuron's receptive field is multiplied by the weight, and then we sum them all to get this neuron's output value. We apply the same filter across a layer, and those values are learned during training. So we feed the classifier a labeled image, it outputs predictions, we math to figure out how wrong those predictions are, and then we math again, nudging each and every single filter in the direction that would have produced a better result. So that's gradient descent. The deep dream process inverts this. So this visualization is recursive. To compute the next frame, we feed the current frame into the network. We start with that photo of Miquel. We then run that image through the network's many layers until we activate the layer that we're interested in. And then we math. How could we adjust the input image to make this layer activate more? And then we adjust the image in that direction. So this process is gradient ascent. Finally, we scale the image up slightly before feeding it back into the network. This keeps the process from fixating on local features, and it also creates this pretty wild zooming effect. Every 100 frames or so, we move to a deeper layer, or a layer to the side. Inception has a lot of layers, and they're not arranged in a neat linear stack. And that gives us this. We started with these rudiments of light and shadow, and then much deeper, we have this city of Kodama situation happening. Shortly, we're going to enter the spider observation zone, in which spiders observe you. But it's okay because the spiders will quickly become corgis, and the corgis are going to become the 70s. Deeper, we find a space of nearly human eyes, which are going to become dog slugs, dog slug birds. Here I found a sort of unfortunate saxophonist teleporter accident. And finally, near the end, we have the flesh zones with the side of lizard. And okay, when I first saw this, I was reminded of nothing so much as Donald Trump. And I resolved to never say that out loud in public until I showed this to my best friend, who said exactly the same thing. And I think this says more about the state of our neural networks, what we're primed to see, than this one. But I do want you to notice and think about what it means that all this skin is so very white. So all of this is pretty trippy. Why is that? What does that mean for something to be trippy? So to figure that out, let's take a look inside ourselves. Meet Scully. Scully doesn't need all this cruft. We are just here to look at Scully's visual system, which starts here in the retina. So Scully's retina, your retinas, our retinas, they're weird. Light comes into them, and it immediately hits this membrane. And there's a layer of ganglions, which we'll get back to later. Ganglions are not particularly photosensitive, but they are the first layer of things that light coming into your retina hits. There's a layer of more stuff that does important things. And then at the back of your retina are the photoreceptors, rods and cones. So light comes in, winds its way through 4 layers of tissue to its ganglion, and hits a photoreceptor. And then that photoreceptor gets excited. It sends out a signal to its ganglions, which then send it somewhere. Where? To an optic nerve that we've drilled right through the center of the eye. So our sensors are mounted backwards, and there's a hole in the center of them, and it's all kind of okay because we can patch up the issues in software. So there's a couple of other problems. One, our retinas have 126 million photoreceptors, give or take. That's 120 million rods, which sense luminance, and 6 million cones, sensing color. And there's about 10 times fewer ganglions than that. 2, the optic nerve has about 10 megabits of bandwidth. It's not really enough. We're trying to send the signal from this 126 megapixel camera through a pipe that's slower than Wi-Fi. And so our retinas do what you might do if faced with that problem. They compress the data. So each ganglion connects to a patch of about 100 photoreceptor cells, which is its receptive field. That's divided into a central disk and a surrounding region. And when there's no light on any of it, the ganglion doesn't fire. When the whole field is illuminated, it starts to fire weakly. And now your ganglions come in 2 species. They're not actually 2 species. They're the same cell behaving in slightly different ways. One kind of ganglion, when the surround is illuminated and the center is dark, about half of your ganglions are going to fire rapidly. The other half aren't going to fire at all. And then the other half of ganglions behave exactly in the opposite way. They fire weakly when their center field is illuminated, or they only fire when their center is illuminated and their surround is dark. And so taken together, if you sort of think about it, it makes sense. This constitutes an edge detection filter. We're doing this processing even in our eyeballs. And it's quite important. This processing lets us downsample the signal from our photoreceptors 100 times while retaining vitally important information, namely where the edges of objects might be. So then the signal goes through the brain. It hits the optic chiasma, where the data streams from your left and right eyes cross, which gives us 3D stereo vision. It's processed by the thalamus, which, amongst other things, is responsible for running your eye's autofocus, something that you definitely have and maybe weren't thinking about up until now. It also integrates with various other sensory inputs from different modalities. So each step of the signal pathway is performing a little bit of signal processing, extracting a little bit of information from the signal. And all of that is before we get to the big visual processing center, the visual cortex, all the way around back here. So our visual cortex is arranged into a stack of neuronal layers. The signal stays relatively spatially oriented through the visual cortex. So there's some slice of tissue in the back of your brain that is responsible for pulling faces out of this particular chunk of your visual field. More or less, brains are a little bit messy. So each neuron in a layer has a receptive field, just some chunk of the entire visual field that it's looking at. Neurons in a given layer respond in the same way to signals within their receptive field, and that operation, distributed over an entire layer of neurons, extracts some feature from the signal. First, simple features, like lines and curves and edges, and then more complex ones, like gradients and surfaces, objects, eyes, faces, motion. It's no accident that we see the same behavior in inception, because convolutional neural networks were inspired by the structure of our visual cortex. Of course, our visual cortex is different from inception in many ways. Inception is a straight shot through. It's one pass from input to output. Our visual cortex contains a lot of feedback loops, these pyramidal neurons that connect deeper layers to earlier ones. Now, these loops allow the results of deeper layers to inform the behavior of previous layers. So, for example, we might turn up the edge detection gain where a later layer detected an object. This lets our visual system adapt and focus, not optically, but attentionally. It gives us the ability to ruminate on visual input even before we become consciously aware of it, improving our predictions over time. And I think you know this feeling. Thinking you see one thing, and then realizing it's something else. So these loopback pyramidal cells in our visual cortex are covered in serotonin receptors. And different kinds of pyramidal cells respond to serotonin differently, but generally they find it exciting. And don't we all? You might be familiar with serotonin from its starring role as the target of typical antidepressants, which are generally serotonin reuptake inhibitors. When serotonin gets released into the brain, they make it stick around longer, thereby treating depression. Some side effects may occur. Most serotonin is actually located in your gut, where it controls bowel movement. It signals to your gut that it's got food in it and should go on and do what it does to food. And that seems to be what the molecule signals throughout your body: resource availability. And for animals with complex societies like ours, those resources can be somewhat more abstract, social resources as well as energetic ones. That your pyramidal cells respond excitedly to serotonin suggests that we focus on that which we believe will nourish us. So it's not correct as a blanket statement to say that pyramidal cells are excited by serotonin. In fact, there's different kinds of serotonin receptors, and their binding produces different effects. So 5-HT1A receptors tend actually to be inhibitory. 5-HT3 receptors are somewhat odd. In the brain, they're associated with sensations of queasiness and anxiety. In the gut, they make it run backwards. Anti-nausea drugs are frequently 5-HT3 antagonists. And there's another kind of serotonin receptor, one that the pyramidal cells of your brain find particularly exciting. This is the 5-HT2A receptor. It's the primary target for every known psychedelic drug. It is what enables our brains to create psychedelic experiences. So you go to a show, and you eat a little piece of paper, and that piece of paper makes its way down into your stomach where it dissolves, releasing molecules of LSD into your gut. Now, LSD does not bind to 5-HT3 receptors. So if you're feeling butterflies in your stomach, it's just because you're excited for what's going to happen. And what's going to happen is this: the lysergic acid diethylamide will diffuse into your blood. LSD has no trouble crossing the blood-brain barrier because it's tiny but powerful, like you. It will diffuse deep into your brain, into your visual cortex, where it finds a pyramidal 5-HT2A receptor and locks into place. The molecule stays bound for around 221 minutes. It's 4 hours, which is a very long time for receptor binding. They think that a couple of proteins sort of get attracted and lock into place, forming a lid over top of the receptor, trapping the LSD inside, which would help explain why it's so very potent, with typical doses about 1,000 times less than most other drugs. So while it's rattling around in there, the little LSD molecule is stimulating a feedback loop in your visual cortex. It's sending a signal that says, pay attention. What you're looking at may be nourishing. It might be important. And so the pattern-finding machinery in your cortex starts to run over time and at different rates. In one moment, the pattern in a tapestry seems to extend into the world beyond it. In the next, it's the trees that are growing and breathing, the movement of visual perception that's been allowed to grow wild. With Deep Dream, we asked what would excite some layer of inception, and then we adjusted the input image in that direction. Now, there's no comparable gradient ascent process in the biological psychedelic experience, and that's because we aren't looking at a source image. We're looking at the output of the network. We are the output of the network. The output of your visual cortex is a signal carrying visual perceptions, kind of proto-qualia, which are going to be integrated by other circuits in your brain to produce your next moment of experience. Now, inception never gets that far. We never even run it all the way to the classification stage. We never ask it what it sees in all this. But we could. In fact, we could perform the amplification process on a final result rather than an intermediate one. Maybe we ask, what would it take for you to see this banana as a toaster? Or, stay with me, don't these skiers look like a dog? So these are adversarial examples, images that have been tuned to give classifiers frank hallucinations, the confident belief that they're seeing something that just isn't there. And they're not completely wild, these robot delusions. I mean, that sticker really does look quite a lot like a toaster, and it's very shiny. And those two skiers they have 4 legs, which is dog-like, and you can kind of see the head on the left and like the tail on the right, and it's very dodgy. A person might look at them and see if they're very tired and far away and drunk. For a second, they might think that they're looking at a big dog. Maybe. But they definitely wouldn't conclude that it's a big dog. Because the recurrent properties of our visual cortex, and not to mention much of the rest of our brain, means that our sense of the world is stateful. It's a continuously refined hypothesis whose state is held by the state of our neurons. Lisa Sabor, preparing us for capsule networks, writes that a parse tree is carved out of a fixed multi-layer neural network, like a sculpture is carved from rock. So our perceptions here are a process of continuous refinement, which may point the way towards more robust recognition architectures, recurrent convolutional neural networks that ruminate upon images, making better classifications or providing a signal that something is off about an input. There are adversarial examples for the human visual system, after all, and we call them optical illusions. And they feel very weird to look at. Like in this image, we can feel our sensory interpretation of the scene flipping between 3 alternatives: a little box in front of a big one, a box in a corner, and a box missing one. And then in this Munker illusion, there is something scintillating about the colors of the dots, which are, of course, all the same. If we design convolutional neural networks with recurrence, they could exhibit such behavior as well, which maybe doesn't sound so great. Like, let's make our image classifiers vacillating and uncertain. But it's our ability to hem and haw and reconsider our own perceptions at many levels that gives our perceptual system tremendous robustness. Paradoxically, being able to second-guess ourselves allows us greater confidence in our predictions. We are doing science in every moment, the cells of our brain continuously reconsidering and refining shifting hypotheses about the state of the world, which gives us the incredible ability to adapt act and operate within an extreme range of conditions, even while we're tripping face, or while asleep. 2, dreams. These are not real people. These are the photos of fake celebrities, which have been dreamt up by a generative adversarial network, a pair of networks that are particularly creative. The networks get better through continuous mutual refinement. And it works like this. On the one side, we have the creator. This is a deep learning network not unlike Inception, but trained to run in reverse. This network we feed with noise, literally, just a bunch of random numbers. And it learns to generate images from that. But it has no way to learn how to play that game. It doesn't know what a plausible image looks like. It lacks a gradient without another network, without an opponent, the adversary. So the adversary is also an image classifier like Inception, but it's trained on only 2 classes, real and fake. And its job is to distinguish the creator's forgeries from true faces. So we feed this network with ground truth. We train it on actual examples of celebrity faces, and the adversary learns. And then we use those results to train the creator. If it makes a satisfying forgery that passes through the adversary, then it's doing well. If its forgeries are detected, then we backpropagate that failure so that it may learn. Now, I should tell you that the technical names for these networks are the generator and the discriminator. I changed the names because names are important and powerful and also meaningless. They don't change the structure of the training methodology, which is incredibly powerful, a semi-supervised learning technique. We haven't gone and taken a huge data set of possible generated images and labeled them as plausible and implausible. No, that would be an impossible task. Instead, we have this process of recursive co-training, where 2 circuits are playing a game, ruminating on a space of possibilities, and so extracting maximum value from a small amount of training data. This process is perhaps helpful for neural circuits of all kinds, though it does have a few quirks. GANs are not so great at global structure. This is Fallout Cow. Here it's grown a cow with an extra body, just as you may have spent a night walking through a house that is your house, but with many extra rooms. And the networks are not particularly great at counting either, counting being a reduce operation. You can kind of imagine why they're not great at it. Here we have a monkey with 8 eyes because sometimes science goes too far. And do something for me. Next time you think you're awake, which I think is now, presumably, count your fingers just to be sure. And if you find right now that you have more or fewer than you expected, don't wake up just yet because we're not quite done. So another interesting thing about this training methodology is that the generator is being fed noise, a vector of noise, some random point in a very high-dimensional space. And so it learns a mapping between that space and its generation target, in this case, faces. And so if we take a point in that space and we drag it around, we get this, which is also pretty trippy. It resembles things that I've seen, that someone who isn't me has seen on acid. It resembles the sorts of things that you may have seen in long-forgotten dreams. And I do not have a magic school bus ride to take us on to understand why that is, but I do have a theory. And that theory is, when we see a face, a bunch of neurons in our brain light up and begin resonating a signal, which is the feeling of looking at that particular face. Taken together, all of the neurons that participate in face detection produce a vector embedding, a mapping from faces to positions in some high-dimensional face space. And as we drag around the generator's vector here, so too are we dragging around our own, which is a novel and somewhat unsettling sensation. So that's a wild theory, but it's not without neurocognitive precedent. So here, we have a rat in a cage. We've hooked an electrode up to a particular region, a particular neuron in the rat's brain. And those pink dots are the locations where it's firing. So if we speed this up, a pattern is going to start to emerge. That neuron is a grid cell, so named because the centers of its firing fields produce a triangular grid. Now, there's a lot of different grid cells in your brain, each aligning to a slightly different grid. They collect data from your visual system and from head direction cells, which similarly encode a quaternion for your head. And together, they construct an encoding of our position in 2D Euclidean space. This operates even in our sleep. If earlier you discover that you're dreaming, and you want to see the end of this talk, but you're having trouble staying asleep, neuronauts, people who specialize in lucid dreaming, recommend spinning around. This detaches your perceived body, the one with 12 fingers and 3 extra bedrooms, from your physical body, which is lying asleep in bed right now. So this positioning system is something which on some level you always knew existed. After all, you have a sense of space as you move through it. You know where you are. And it's likely, even necessary, if we believe that cognition is computation, that our qualitative sense of position has a neurocognitive precursor, a signal in the web that tells us where we're at, in many senses of the word. Part 3, sticks and stones. And they say you can't tickle yourself because you know it's coming. Specifically, when your brain sends an action command to your muscles, that's called an efference. When an efference is sent, your brain makes a copy. And it makes a copy sounds so planned, so engineered. Your brain is this big, messy, evolved signal processing mesh. And so another way to think of efference copies is as reflections. So we take the efference and we send it out to our peripheral nerves, where presumably it's going to make some muscles contract. Meanwhile, from the efference copy, we predict how our body's state will change. And we use that to update our brain's model of our body's state. Now, if we didn't do this, then we would have to wait for sensory data to come back from our peripheral neurons to tell us what happened, like where is our hand right now? And then we would face the same problem as trying to play a twitchy video game over a crap connection. Signals take about 10 milliseconds to go from our brain to our periphery, and another 10 milliseconds to travel back. Our body, our nervous system, is not that low latency. And so to enable smooth, coordinated movements, our brain has to make predictions. So life goes on. But in a moment, we have a problem, because we will still receive sense data from our nerves. If we updated our models again, they would actually fall out of sync. This is the double applied server report problem. Solving it between a client and server, we might tag the data somehow, but our brain doesn't really have a unique ID counter. So the model is more complex, but it does result in the signal being attenuated, which keeps our model in sync. So this attenuation applies to our sense of touch as well, when that touch is an expected consequence of our own movement. So this is clearly quite a complex model, and aspects of it are likely distributed throughout the brain. But there's one place that's particularly important in maintaining and executing it: the cerebellum. The cerebellum is quite special. It contains half the neurons in our nervous system. All action commands from the brain to the body route through it, and all sensations from the body to the brain as well. It's long been recognized as vitally important to motor coordination, like this. People with cerebellar damage have difficulty performing this action smoothly. With cerebellar damage, our movements become jerky, laggy. It's been theorized that the cerebellum acts as a Smith predictor, our brain's controller for our latency-distant bodies, able to estimate the body's current state, integrate sensory feedback to update that model, and decompose gross actions generated elsewhere in our brain into a fine-tuned, continuously adjusted control signal. And once you've evolved it, such a thing has many uses. There's a growing body of evidence implicating the cerebellum in language, which does make sense. Utterance is a kind of movement, and language, she said, gesticulating wildly, is not limited to utterance. The work of moving words is not so different from the work of moving the body. They are both transformations, from the space of internal states, efferents, and ideas, to the space of world coordinates and external sense impressions and other people, and back again. And what happens when this predictor encounters a problem? Oh, I just realized I need sound. Is this going to happen? I can do this. So what happens when this predictor encounters a problem? When there's an irreconcilable discontinuity in the model? So these things are not so different. They're both very visceral actions. They're guttural, and they shake our bones. And jokes, similarly, are shaped like trauma. They're both shatterings, the illuminations of discontinuities. They're paradoxes, things which cannot be, and yet are. Things which we must revisit again and again, churning, water smoothing the edges of cutting stone, the machinery of our brains trying to make sense of a world that resists it. So preparing this talk has been a kind of difficult time for me. I didn't think I could do it. The world seems to be falling apart. I got dumped, which didn't help. There were days when I would open my email and every subject line would be a stone, and I would think to put them all into my dress and wade out into the sea. But I didn't, because I remembered that I am a process of creation. I am a song singing myself. We are stories telling ourselves, a sea understanding itself. Our churning waves create every exquisite moment of joy and agony and everything else. It's you. It's all you. You are everything. Everything you have ever seen, in every place you have ever been, every song you have ever sung, every God you have ever prayed to, every person you have ever loved, and the boundaries between them and you and the sea and the stars are all in your head. Thank you. That's all? Oh, now it comes out.
Are there any questions? Well, if there are no more questions, we can thank Ashi.
Thank you, everyone. You feel free to reach out to me on Twitter if you do have any questions. Oh, yeah.
What do you use to create these slides?
That is actually the most common question. JavaScript is the answer. Well, the web. I use the web. It's a website. Yeah, here's Chrome. So all those web technologies, yeah. A lot of CSS, actually.
Hi, Ashi.
Hi.
Thank you so much for an incredible talk.
Thank you.
What is the next step? How do we take another step closer between reconciling biological computation and where we are in, be it deep learning or electronic computation?
I think we're taking a lot of the next steps right now. So there are projects to simulate parts of the brain. There's a project, I think a subproject of the Connectome research group, which has simulated like a tiny chunk of a rat brain. And all of these simulations it's a little bit hard, right? Because we actually can't measure the actual data to know how good the simulation is. And so you have to kind of figure out proxies to evaluate your models. But more of that kind of work, I think that kind of work is one avenue, and then getting better imaging technology is another. And I think we have okay access through fMRIs. A lot of that data is like really heavily massaged, and it's like quite hard because you have a very thick skull. That's the problem. We have thick skulls. But I have a suspicion that in the next 20 years, the time horizon that makes anything possible in futurism, we're going to see like really significant advances in nanotechnology that'll make that kind of imaging better. Like you can imagine really smart dyes that can sort of align to an externally presented magnetic field and give us a lot of insight into when neurons are firing, when membranes are depolarizing. And that's going to be the other avenue that I think really blows it open.
So the biggest difference between a machine and a computer is that the human could do causal analysis. So there's been work done on causal inference as well for machines. Is this one route that you think would work out?
To get machines to do causal inference?
Yes.
I think, well, maybe. I don't understand that problem space very well, but I think one thing that separates the machinery of our experience from most of these machine learning systems is that we are deeply, deeply recurrent. Like our parts of our brain are wired in loops all over the place, which is why we have sort of a continuous experience, like why one moment like leads to the next moment. And we haven't, I think, even really tried to do that in machine learning models, in part because recurrent models are famously hard to train. I'm sure there's techniques for that are improving all the time. But we have a lot of training data, like hundreds of millions of terabytes of input data from a robot walking around in a world. And then also all this like social cueing. And so just getting the amount of training data required to train sort of a recurrent system like our brains that can do the kinds of causal analysis that our brains can do, which if you think about it is sort of, it comes out of having a narrative structure. Like I kind of exist because my brain is trying to figure out why my body is doing all these things. And it's like, oh, I must be an agent with moral responsibility. So yeah, I think we can get there, but I think we need like another order of magnitude of training data and probably better techniques.
Hi, thanks for your talk. I like the framework you used. My question is about what you think about the consistency of interpretation that you would expect from people when they look at the outputs of a model or something like that. Like we try to build a lot of models that we expect will do certain things, but I think there's a lot of variability in terms of how people will look at those results, whether it's a customer, whether it's internally. And so have you thought about that concept in general, like the variability of how the brain parses the outputs of some of these things, and whether you can design a model that would be consistently interpreted by everybody, or whether there's always going to be debate?
Oh, that's really interesting. So in this case, you're sort of asking about the people who are looking at the results of some statistical model will interpret it and they bring their own biases, right? There's another act of modeling, basically. And can we train a model to, and this is where I'm not clear, can we train a model to do what? To produce a certain internal representation within the people who read it, basically?
Yeah, like, can you can you account for that, or are you basically, you have no control over that second process, and so you're always going to have like, you contribute half of the equation and the recipient contributes the other half? You know?
I mean, it's really fascinating. I think you can. You just have to include that in your training paradigm. Like, you could imagine a system where you don't produce the output of your model, or the feedback criteria for your model is actually like, what action do people looking at the report think is right? And it would be interesting to get training data for that. You could maybe imagine getting training data for that just by doing some kind of historical analysis. So you take, I don't know, stock data, and you're like, by showing this screen to a human, the human should make the right decisions, and you know what those decisions should have been. And so then you train a model to basically manipulate whoever is looking at it. I think you should ask Facebook about this. They seem to be really, really, at least, they seem to be good at that, or they seem to be working on it.
Oh my God, that's too good. I don't know. What about a machine that can think about questions to ask by itself and query the world for questions that it needs to answer to get a better prediction? Like it will ask the question, not the human.
Yeah, so this would be something like determining that there's really high, it basically doesn't, the current model doesn't have enough resolving power along some dimension.
And it knows what it wants to get that resolution. And
yeah, something we don't have much of at all is sort of hierarchical machine learning systems. I think, I'm sure someone's doing research into this, but where it can sort of decompose problems, it can decompose a large-scale goal into sub-problems. We are mostly doing that kind of architectural work now, in like by hand, in how we architect these systems. The only thing I can think of is that there was a recent paper from Google where they had some model construct a different model or like optimize a different model for a problem. And so I think that's perhaps the tip of that iceberg. But yeah, hugely unexplored.
Okay, great. Thank you, everybody. That's all the time we have for questions. Let's thank Ashi again.
Thanks, everyone.